Hello again. This is video lecture 16.1. So we are starting chapter 16. And the title of chapter 16 is Waves Part 1. In other words, this is going to be a two-chapter sequence in which we will study the phenomena known as waves. And there's a reason that the two chapters on waves are immediately following the chapter on oscillations, chapter 15. Because waves are a bunch of oscillations in a material, at least the kinds of waves that we're going to be studying. So we're going to be using a lot of the ideas from chapter 15 in chapters 16 and 17. So let's start with chapter 16, section 1. And first, just some terminology. And we don't really do a lot of this in physics, where we just say terms. But wave phenomena are very common in nature and very diverse in their characteristics. And so we have a lot of different terms to describe the different kinds of waves we observe in nature. So it's a little bit difficult to avoid just stating some terms at the beginning. And chapter 16, section 1, is going to focus on one category of wave called a transverse wave. And we'll have to explain what we mean by that. And the whole chapter, chapter 16 and 17, is about a category of waves known as a mechanical wave. And my description of a mechanical wave, that's this key idea, is that it is, at least in a description, an extended disturbance of a medium that contains energy. So a medium is a physical thing upon which this disturbance is going to travel, generally speaking, or propagate. And this disturbance on the medium is going to contain energy. Probably the simplest thing to visualize, to picture in your mind at the outset, is waves that you see in water. Whether it's a small body of water like a bathtub or a sink, or a large body of water like a lake or a sea or an ocean. We all have seen waves on water. That's a mechanical wave. The water is the medium. You can have a situation, probably easier to do, say, in a bathtub, where the water is completely calm and that the medium is undisturbed. But then if there's something disturbing the medium, then you see the water level going up and down. It's that disturbance of the water that is the wave, okay? And in a mechanical wave, this disturbance is extended. It's spread out throughout the medium. And another key thing, it contains energy. You don't have to think very long to think of an example of a wave on water and how you can notice how it contains energy. Think of the destructive capabilities of a tidal wave. And it doesn't take you very long to realize, oh yes, waves contain energy. Now, more terminology. This whole chapter and chapter 17 is about mechanical waves, where we're going to have a disturbance in a medium. It's going to be an extended disturbance, and it's going to contain energy. But we're going to take those mechanical waves and we're going to further categorize them as traveling waves or standing waves. In a traveling wave, the energy associated with the wave propagates throughout the medium. I say there's space, but I could also say throughout the medium. Okay, in a mechanical wave, we need a medium to be disturbed. And it's that disturbance in the medium that's propagating throughout space if you have a traveling wave. You could have a standing wave, where the energy associated with the wave does not propagate throughout the medium. So in a traveling wave, the energy associated with the disturbance travels throughout the medium, and in a standing wave, the energy associated with the disturbance does not travel throughout the medium. We'll be showing you pictures and animations so that you can see that. Okay, now, within the categories of traveling and standing waves, we have further subcategories. This is because All these terms is just because of the richness of phenomena, wave phenomena that we observe in nature. So let's go back to traveling waves. Those can be categorized two ways: a transverse traveling wave or a longitudinal traveling wave. Of course, the same thing will be true for standing waves. You can have transverse standing waves and longitudinal standing waves. Let's look at traveling waves first. Transverse traveling wave sounds technical. Here's what it means. The disturbance of the medium is perpendicular to the direction in which the wave travels, the key word being perpendicular. The disturbance of the medium is perpendicular to the direction in which the wave travels. That will be studied. A transverse traveling wave will be studied in chapter 16. And I'll show you a picture and then an animation. A longitudinal traveling wave is one in which the disturbance of the medium is parallel to the direction in which the wave travels, the key word being parallel. And we're going to study longitudinal traveling waves in chapter 17. Then for standing waves, you can have transverse standing waves, where the disturbance of the medium is perpendicular to the direction of the wave, and you can have longitudinal standing waves, in which the disturbance of the medium is parallel to the wave. Let me start with just some static pictures before I show you animations. I just took a couple of pictures right out of the book. Top picture is showing a way to make a transverse traveling wave. What is this picture trying to describe? This wave, this mechanical wave that we're showing in this picture, is created on the medium of a string or rope. And what we've done is we've taken a rope and we've tied one end of it to a fixed wall or support of some kind. That's along there on the right. And we're holding the other end. And if the medium, the string or rope, is undisturbed, the rope would just would just hang there horizontally. I'm holding it under tension with my hand there at the left end. And it would just lie right along the x-axis, and it would be undisturbed, no wave at all. But then all I have to do to make a transverse traveling wave is move my hand up and down a little bit, perpendicular to the horizontal direction. We'll take horizontal to be the x-axis, and we'll take perpendicular, vertical, to be the y-axis. So undisturbed, the string will lie along the x-axis. I will make the disturbance, the wave, by simply moving my hand perpendicular to the x-axis in the y direction. And we'll get a wave or a wave pulse in the rope, and that's what this curved part of the rope looks like. That's the disturbance. That's the wave. And because the rope is under tension, this disturbance will be observed to propagate to the right with a velocity that we'll just denote v. We've been using v for velocity. Here it means the velocity of the wave, the disturbance on the medium, the rope. And that's how you make a transverse traveling wave. The disturbance of the rope is in the y direction, the actual rope itself, but as we watch that disturbance, it travels in the x direction. Now let me show you how to make a longitudinal traveling wave. You can't really do that on a rope, okay? But you could do it in a column of air. And that's what this next little schematic shows, okay? This thing right here is a column of air, like you might see on an organ pipe, but laid on its side. And we fitted in at one end a tight-fitting piston kind of an object with a handle. Now, if there's no disturbance, the air in the column is uniformly distributed. The air molecules are uniformly distributed throughout that column inside there, and we have no wave, no disturbance at all. But if I start moving that piston at the left end back and forth, left and right, then I'm going to disturb the air molecules, at least the ones right up against the piston, bunch them up, and they'll then interact collide off their neighboring air molecules, and what will happen is this disturbance in the distribution of the air molecules will propagate, in this case, to the right. And I will have a wave traveling with a velocity v to the right. But the air molecules themselves, and the air is the medium, are being disturbed back and forth, jiggling, if you like, back and forth. That's a longitudinal traveling wave, where the disturbance of the medium is in the same direction as the wave is traveling. So these two simple schematics show a transverse traveling wave on a rope and a longitudinal traveling wave in air. And in essence, this top picture is going to be the focus of our studies in chapter 16. And this bottom picture is going to be the focus of our studies in chapter 17. All right, that's just some simple schematics of transverse and longitudinal traveling waves. Now I've given you all this terminology, let me kind of hone in on the specific kind of wave we're going to be studying for the most part in this chapter. And that is right here, a transverse traveling wave on a taut string. Remember, taut means we're holding that string under tension. There's some tension in the string. That's what taut, T-A-U-T, means. So here's what we're imagining. We're simply starting with a long, uniform, taut string. Really long. So long that I'm not even worried about what's happening at the other end of it. It's a uniform string. Its mass is distributed out uniformly. And it's taut. It's got some tension that it's under. And another important property of the string has to do with its inertia. And that's what we're going to call its mass per unit length. Now, we got to get used to that in this chapter. That's what is the convenient inertia property of the medium, the mass per unit length. I don't care so much about the total mass of the whole string. I want to know how much mass per unit length it has. And in SI units, that would be kilogram per meter. In other words, how much mass in kilograms does every meter of the string have? That turns out to be the useful quantity to describe the inertia of the medium that the wave is going to travel in. Note the symbol for mass per unit length. Please note, that's not an M. That's a Greek lowercase letter mu. That's what we're going to use to describe mass per unit length. Note the SI unit would be kilogram per meter. You'll also hear that quantity called linear mass density. Mass per unit length, mu. How much mass in kilograms does every meter of the string have? Now, when undisturbed, the string lies along an x-axis, just right on the x-axis. But we're going to make a disturbance. We're going to have a disturbance, and that disturbance is going to move the string perpendicular to the x-axis. We'll call the perpendicular direction the y direction. And that disturbance then propagates along the string at a speed v. So let me show you my first animation of a transverse traveling wave from Wiley+. Okay, so here we have a picture that we're gonna run an animation here in just a second. But what you're supposed to visualize, well, you can see there's an x-axis with numbers in centimeters, and then a y-axis with numbers in millimeters. Yes, different scales. And if you look carefully, there's like an orange line along the x-axis. That represents a string, an undisturbed string, just sitting on the x-axis. And we have painted one little piece of the string red with some red paint, and that's that red dot that you see on the animation. Now the red dot happens to be resting at a location x equals 2 centimeters. Now that's an undisturbed string. There is no wave yet. All right, so here's what's happened. someone or some device way over to the left of our field of view has simply moved the string up along Y and back down again. That's made a disturbance. And then neighboring pieces of string, through their tension, tug on each other, and that's how the disturbance propagates. And it's going to propagate to the right. See the arrow that says disturbance propagates and it points to the right? And this animation is going to it tells you the speed of that propagation, v to the right, 2 centimeters every second. So I'm going to run the animation. I want you to watch for the propagation come in to the field of view from the left. And first I just want you to watch the disturbance itself propagate in the plus x direction. Here we go. There's the disturbance in the string, and it's propagating to the right in plus x at a speed of 2 centimeters per second. That's a transverse traveling wave. Some people would call it a wave pulse, but that's okay. Now what I want to do, I'm going to run it again. Now I want you to focus on that red dot, because that's just one particular piece of the string, and I want us to focus on how that piece of string moves. Focus on the red dot. And it moves up and then down. So any particular piece of string, such as the one painted with the red dot, merely moves in the y direction, up and down. Like right there. We'll freeze it. Okay? Our piece of string with the red dot is moved up in the y direction, roughly 1 millimeter, and the red arrow is its actual velocity, which is up. So any particular piece of string moves in the y direction, but the disturbance moves in the x direction. So we got to be careful. There's the disturbance, that's traveling in the x direction, and then there's what any particular piece of the string does, and that's moving the y direction. That's what happens in a transverse wave. Now what I can do in this animation is change the v of the disturbance, the wave. The biggest I can make it is a v of 5 centimeters per second. All right, now I want us to watch. First, focus on the disturbance traveling to the right. Sure enough, it travels faster. Okay? It travels to the right at 5 centimeters per second. If I focus on the very top of the disturbance, and I focus on how far it travels in 1 second, the top of that disturbance travels from x equals 0 to x equals 5 in a time of 1 second. So the disturbance is traveling 5 centimeters to the right every second. But again, any particular piece of string, such as the piece painted with the red dot, travels up and down. Okay? Okay, so there's the v of the disturbance. In this case, that v is directed to the right. And we can control that with this slider labeled v. Okay. That's my first animation. And that's a transverse traveling wave. Now let me go back to my notes. And now let me further specialize what we're going to study. Okay? A special case of a transverse traveling wave. What we call a sinusoidal transverse traveling wave. Yes, I know there's lots of terminology. But that's going to probably be the most important kind of wave for this chapter. A sinusoidal transverse traveling wave. That's what happens when one end of the string moves in the y direction with simple harmonic motion. I told you chapter 15 is going to be important because that's what we studied in chapter 15, simple harmonic motion. So let me show you a different animation of a sinusoidal transverse traveling wave. So I need to get over to Wiley Plus and change the animation. Okay, now what are we seeing? We started with a rope or string that, when undisturbed, would just lie along the x-axis, and that string has a mass per unit length mu in kilogram per meter, and it's under some amount of tension. And then, way over on the left way outside the field of view, I am taking that left end of that string and moving it up and down in the y direction with simple harmonic motion in the y direction. And that has been happening for a very long time. Okay? Well before what we see here. And now that that's been happening for a very long time, here's a freeze frame at one instant in time, t equals 0. Okay? And that is a snapshot at a particular moment in time of this sinusoidal, transverse, traveling wave. Do you see why it's called a sinusoidal, transverse, traveling wave? Look at the shape. It's a sine curve. At this snapshot in time, t equals 0, that is exactly a sine wave, a sine curve. Okay? So this snapshot graph, if you like, a snapshot in time, shows us exactly what the string looks like at t equals 0. It looks like a sine wave. And that's why we call it a sinusoidal wave. But there's no mystery how you make it. You take one end of the rope and you move it in the y direction, up and down, with simple harmonic motion. Now, if I run the animation, first I want you to just kind of watch it, and I want you to see why it says disturbance propagates and the arrow points to the right. Because, at least to my eyes, when I look at this animation, when I run it, when I let the time proceed, it sure looks to me like there's a motion to the right. So let's just run the animation. Okay? To me, it looks like there's motion to the right. And there is a disturbance that's propagating to the right. But let me emphasize now, by resetting it, that the rope itself is not traveling to the right. And how do I know that? There's a red dot again. You see it? I painted a red dot on a little piece of that rope. Now I want you to watch what that red dot does, because that tells you what that piece of rope is doing. That red dot moves merely up and down in the y direction. And in fact, it moves up and down with simple harmonic motion. That's really important to note, that any particular piece of the string, such as the one painted with the red dot, moves up and down with simple harmonic motion. Okay, that's the kind of wave we are studying. So now let me go back and start to describe that wave mathematically. Yep, we're going to describe that wave mathematically. What it boils down to is I want a function that will tell me the y disturbance. How much up or down is any piece of string disturbed by the wave if you tell me x and t. Where would the string be on the x-axis if it were at rest? And what's the value of t on the clock? Then I'll tell you why, how much that piece of string has been disturbed up or down. That's my goal. That's what I want. All right, so how are we going to do that? Well, first, I'm going to start by just telling you this function y. So what I'm about to show you on the screen is going to take a little getting used to. But it's a function. I want to know the output y, and it's a function of two variables. There are two inputs, two variable inputs, x and t. You tell me where on the x-axis, okay, somewhere is the origin, and there's this rope, let me draw it in red, that would normally just be at rest on the x-axis. And you tell me what point on the x-axis you're interested in, and what value t is. And you input those two things into this function over here, and the output will be the y value. How far up or down has that particular piece of string been displaced? And this function y, if you want to be really fancy, that describes the displacement of the medium of the wave is called a wave function. Note then, there are two independent variables, x and t, two things you got to input, you got to tell me. Where are you on the x-axis and what is t? And there'll be one output, the dependent variable, y. How much has that piece of string at that x and t been displaced up or down? Are you ready for the function? I'm just going to state it to you. But here's a hint. We call this a sinusoidal transverse traveling wave. So guess what the function's going to be? It's going to be a sine function. You could also use cosine, by the way, but this book uses sine. Here is the function. Okay? The wave function that describes a transverse sinusoidal traveling wave, such as shown in the previous animation. Right here. Now there's a lot going on here, and we're going to have to unpack it. But that's the function. Y of x and t equals y max sine of kx minus omega t plus phi. First, let me go through and circle all the things that are constants in this wave function. This symbol y max is a constant. The symbol k is a constant. The symbol omega is a constant. Yes, that's the same omega we used in chapter 15. The symbol phi is a constant. Yes, that's the same phi we used in chapter 15. And yes, the y max is like the x max in chapter 15. The only symbol that's new here that is not the same as in chapter 15 is k. And no, k doesn't mean a spring constant, I'm afraid. But those are all constants in this function. Y max, k, omega, and phi. The variables, let me get rid of some of this stuff. The variables are x and t, the independent variables. So we're going to need to understand this function. So let's go through some of the key points. Let me emphasize something I've already said. The wave disturbance travels in the plus x direction, while the medium itself oscillates parallel to the y direction, the rope or string. First term, the amplitude of the wave. That's the maximum displacement from equilibrium. That's the y max symbol out front, and the SI unit is meter. That's this right here. That's the maximum y displacement of any piece of string, and it's called the amplitude of the wave. And I know it represents the maximum displacement of any piece of string because the sine function, its output, can only oscillate between +1 and -1. So if I multiply that sine by a constant called y max, then the biggest the y can be is between plus ym and minus ym. That's called the amplitude of the wave, SI unit meter. How about the omega? Same name as chapter 15, the angular frequency of the wave. Same units as chapter 15, radian per second. And here's a tip that's a very helpful thing to remember. Every piece of string moves parallel to the y-axis with simple harmonic motion, and the period of that simple harmonic motion, capital T, is related to the angular frequency omega by capital T equals 2 pi over omega. Okay? All right, what I want to do is start to put some numbers on these quantities, these constants that describe the wave, by going back and forth between this slide, or my slides, and the animation. So first, let's look at the animation and get a number for the amplitude for that sinusoidal wave. So let's go back to the animation. There it is. Look, zoom in with your young eyes and look carefully at the animation. Can you see what the y maximum is? That'd be the amplitude of the wave. What's the maximum y displacement of any piece of string? You can look at our snapshot there at t equals 0. Can you see what it is? It's 2 on the y-axis. Note the units, though, on the y-axis are millimeters. So let me go back to my notes, and let me scroll down here where I've got a little bit of room, and let me write this. So based on the animation, the amplitude of the wave, y max, is 2 millimeters. That's just by observation. If you want to convert that to meters, you may. It's 0.002 meters. That's the amplitude. Okay? All right. Next thing I want to do is estimate the angular frequency of the wave in radians per second, omega. How are we going to do that? Well, omega, angular frequency, is equal to 2 pi over the period. And the period is the repeat time, if you look at any piece of string, to go up and down and complete its cycle once. So let's go back to the animation and watch it, and watch that red dot go up and down through one cycle and estimate the period. So I'm starting at time 0. Look where the red dot is. It's right on the x-axis. And as I drag the slider, it's going down. It goes up to its highest point, and now it's coming back down, and right about there, whoops, I just passed it. Right about there, it is just back to where it started. Look how much time has passed on this animation. 2, that would be in seconds. So we have a period of 2 seconds. So let's go back to our notes, and let's put in that this is 2 pi. By the way, that's a radian with that 2 pi. And the period t is 2 seconds. The 2's cancel. Oops, pardon me. 2 pi. The 2's cancel. And I'm left with an angular frequency of pi radians per second for that particular sinusoidal wave. All right, now let me go back up to the next constant in the wave function to describe. And this is the new one for this chapter, and it takes some getting used to. I'll tell you its name in the book, although the name doesn't help you much understanding it. It's that constant k inside the argument of the wave function, and it's called the angular wave number of the wave. It's related to the angular frequency omega. They're like cousins. It's called the angular wave number, symbol k. The SI unit is radian per second. Notice angular frequency had a SI unit of radian over an amount of time, radian per second. This cousin to omega, this so-called angular wave number, has an SI unit of radian over a distance, radian per meter. Now, here's a tip about how to think about angular wave number. First of all, the shortest repeat distance of the wave is called its wavelength, and there's a symbol for that. It's a Greek lowercase symbol, lambda. Let's go back to the animation and see that. I've marked it, in fact, in the animation with the 2 black dashed lines and the double-headed arrow connecting them. That's the shortest repeat distance of the wave. From one zero crossing going upward, where the red dot is, to the next 0 crossing going upward. That is the shortest repeat distance of the wave, and it's called the wave length, lambda. Okay? And the animation shows me at the top with the slider that the repeat distance lambda, the wavelength, is 2 centimeters. And if you look very carefully on the x-axis, that does appear to be the distance between those 2 black dashed lines. Okay, now, why am I telling you that? Because, back to the slides, the angular wave number is related to the wavelength by this handy formula. Wavelength equals 2 pi over angular wave number. Note another way to write that is angular wave number k is 2 pi over wavelength. Just like angular frequency, omega, is 2 pi over period. I told you omega and k are like cousins. If the angular frequency is 2 pi over the repeat time, the angular wave number is 2 pi over the repeat distance. 2 pi over period, 2 pi over wavelength. Omega, k. The unit of k is radian per meter. Let's get the value of k for our sinusoidal wave. Let's figure it out. Its value. K. Angular wave number. Well, that's 2 pi over the repeat length of the wave, lambda. And our animation told us what the wavelength was. So we have 2 pi, let's put in the unit for that, radian. Remember the wavelength is 2 centimeters, be careful, put that into SI, 0.02 meters. And I think the simplest way, if you work that out on your calculator, you see it's 100 pi, radian per meter. Okay? That's the value for the angular wave number for that wave. You might not have much intuition for it, but just think of it as the cousin to the angular frequency omega. And whereas omega is 2 pi over the repeat time, 2 pi over the period, k is 2 pi over the repeat distance, 2 pi over the wavelength. Okay? The more rapidly the waving and over the shorter distance, the larger the omega and the k. All right, let's go back to talking about constants in the wave function. So we've talked about the amplitude, y max, the angular frequency, omega, now with the angular wave number, k. The other constant is the phase angle, phi, with the SI unit of radian. Now that we had in chapter 15 when we studied simple harmonic motion. In this context, the phase angle phi tells us how much the wave deviates from a pure sine function at t equals 0. So you look at time 0 and you take a snapshot of the wave function, and if it's a pure sine function, then that phase angle phi is 0. But if it's a sine function that's been shifted left or right, well, then you're going to have a phase angle that's not 0 to deal with. A positive value for the phase angle phi shifts the sine function to the left, and a negative value for phi shifts the sine function to the right. Let's look at our animation and figure out what the phase angle is. Let me go ahead and reset the time to 0. There it is. Now just look at that wave function. Is it a simple sine curve? You need to remember what a simple sine curve looks like. Do you remember what a simple sine curve looks like? That's the kind of sine that you would have learned in trig in high school if you plotted it. Sine x versus x. Looks like that, and it repeats this way too. And that's exactly what our function looks like, our wave function. In other words, for our wave, the phase angle is 0 radians in our animation. All right, now that's it for the constants. That's it for the constants that have to be specified in the wave function, the y max, the k, the omega, the phi. Then the x and t are variables. They're waiting for you to give me values for them. And then we'll plug in and tell you what the y is. But here are 2 more useful relationships that we want to just know. First, the angular frequency, the angular wave number, and the speed of the wave, v, are related to each other with a very simple form. Right there. Angular frequency equals angular wave number times speed of wave. Really, really, really useful when you study a traveling wave. And if that seems like a very odd relationship, let's at least check it by units. Let's check that the units are the same on both sides. Okay? On the left, we have angular frequency, omega. That has SI unit of radian per second. Let's figure out the units of k and v and multiply those units together. I'll do it right over here to the side. K is angular wave number, radian per meter. Multiply that by the units of v. V is a speed. So, meter per second. I have a meter that cancels, and what am I left with? Radian per second, just like on the left. So the units are consistent. Okay? All right. Tell you what, let's then use that equation to learn something more about the wave. So let me start with that formula, omega equals k times v. Let me solve it for v. So v equals omega over k. And let's plug in our numbers we know already for omega and k for this wave. The angular frequency is pi radians per meter. and the angular wave number is 100, radians per second, beg your pardon, pi radians per second, and the angular wave number is 100 pi radian per meter, and the pi's cancel, and 1 over 100 is 0.01, and the units of radians cancel, and sure enough, I have units of meters per second. So that wave is traveling at 0.01 meters per second, or 1 centimeter per second. And if we look back at the animation, look at the slider there in the middle. V in centimeters per second is set at 1. So that seems right. Okay, back to the notes. Here's another useful relationship that follows right from the one I just mentioned, from omega equals k times v. Given that omega equals 2 pi times the frequency f, and k, angular wave number, equals 2 pi over the wavelength, you can substitute those expressions. 2 pi f here for the omega, and 2 pi over lambda there for the k. And when you simplify, you get this simple formula that's also very useful for a traveling wave. The frequency of the wave, f, equals the speed of the wave over the wavelength. Let's check that one with our wave in our animation. First, let's get the frequency, f, for our wave. F. Let's not confuse f with omega. F is omega divided by 2 pi. To be clear, it's omega divided by 2 pi radians. Our omega is pi radians per second. So we divide that by 2 pi radians. Pi's cancel, unit of radian cancels, so I just have a 1 over second, and I have a 1/2, or 0.5, 1 over second, and 1 over second is given the unit hertz. So the frequency of that wave is 1/2 of a hertz. But let's also check this value using that new little useful relationship. Frequency equals speed of wave over wavelength, and plug in those numbers. We just found the speed of the wave, v, is 0.01 meters per second, and we already know the wavelength is 0.02 meters. Unit of meter cancels. I have unit of per second, which is hertz, and 0.01 divided by 0.02 is 0.5 hertz. So either way, you get f equals 1/2 of a hertz. Okay, so we're just studying this sinusoidal wave, okay? Up above. Please note, this wave up above, this wave function, that described the wave in our animation. That wave was traveling in the plus x direction. That's a very important point, okay? This is for a sinusoidal wave traveling in the plus x direction. And watch out for something. Watch out for that minus sign right there inside the argument of the sign. That can throw you. But that is what must be there. There must be a minus sign between the kx and the omega t if you are describing a wave that's traveling in the plus x direction. I can explain to you, it might seem a little abstract, but I can explain to you why that has to be a negative sign if the wave is traveling in the plus x direction. Imagine a point on the wave that's a 0 crossing, where that particular piece of string has not been displaced up or down at all. It's called a node on the wave. Since the sign of 0 is 0, and I already know the phi is 0 for this wave, I'm talking about the location of a node, x node, where the argument of the sine function equals 0, because the sine of 0 is 0. I solve that for the location of that node, and it will tell me that it's omega over k times t. And I can think of that thing in front of the t as how fast the node is propagating and in what direction. And since it's positive, the node is traveling in the positive x direction. What if I have a wave that's traveling in the negative x direction? You could have such a thing. The disturbance is traveling in the negative x direction. What's the appropriate wave function to use in that case? That's what I'm going to show you here. What if we have a wave function that describes a sinusoidal wave traveling in the negative x direction? Watch out. It looks very, very similar to the wave function I've been talking about, with one key difference. There's a plus sign between the kx and the omega t. And that's because, again, if you want to look at one of the node points on the wave, that's where kxn for node plus omega t equals 0, because the sign of 0 is 0. Solve for the location of the node, and you get negative omega over k times t. The negative means the node is traveling in the negative x direction. So watch out. We have to use the appropriate wave function depending upon whether the wave is traveling in the plus x direction or the negative x direction. And you have to get the appropriate plus or minus sign inside there between the kx and the omega t. Okay, now there's one more topic I want to talk about, but I think I'm going to break this up. So I'm going to pause this. I'm going to pause for now. This will be the end of this video, and then I'll have one more because I want to talk about Chapter 16, Section 2. So that will be all for this video.